Welcome to the third dimension. The goals in this section, we want to plot points, planes, and cylinders. We want to find the distance between points in space, and we want to find the equation of a sphere. Okay, so if you think about it, your career in mathematics kind of started with, well, at least in algebra or pre-algebra, started with the real number line, didn't it? So if you think real number line, what do you think about when you think about the real number line? I think about, shape that looks something like that, right? Keeps, it's a line. It keeps going forever to the right and to the left, so we use arrows in the end. And we know that 0 is in here somewhere, right? 1, 2, 3, 4, -1, -2. So let's see. And, you can plot any number in between. So let's see, 1, 2, 3, pi might be here. Pi. And then 1 is here, -1 is here. And it keeps going in both directions. We call this R1. There's one dimension to consider, right? So we actually call that R1. We call the number line and all the numbers that correspond to the number line R1. And then very quickly in algebra, you start talking about R2 when you plot points, right? When you plot ordered pairs. So R2, when you think R2, we usually think about the XY plane. There's no reason why we have to call the horizontal axis X and the vertical axis Y. But we often do. So you might, if you're over a distance of A on the X and up a distance of B on the Y, and you wanted to plot a point that happens to be over A and up B, you can denote it like so. And we call this XY plane R2. There's 2 dimensions to consider, right? 2 coordinates to consider when you plot the ordered pair. Well, we want to talk about R3. So what do we have to do to create a 3-dimensional coordinate system? Might make sense that we need another axis, right? I mean, think about it. To go from R1 to R2, we put in a y-axis like that, right? So maybe if we put in a z-axis through the origin, which is right here, perpendicular to the x and to the y, we'll come up with a way to plot a point in space with 3 coordinates. And that's exactly the idea here. So what might that look like? Okay, you have to start thinking 3-dimensionally here. So I'm going to say this is my z-axis. And then for now, I'm going to think of this guy for now. It's going to change. I'm not going to keep putting the arrows on the end. I'll put them there for now. I'm going to think of this guy as my positive x-axis and then negative x-axis over here. And this guy going into the screen is my positive y-axis, okay, for now. And then if you looked at it from above and you wanted to plot the point AB, you could go over A on the x and over B on the y, and then you could plot that point. It's kind of like the corner of a box. And I'll say more about that in a few minutes. Or if you wanted to plot the point ABC, maybe this distance from the origin is C, you could go up to this corner of the box, as long as you're up a distance of C. So this distance here to here should look the same as this distance here to here. I'll say more about that in just a minute. So this is what we call R3. A point could have coordinates A, B, and C. That's x equals A, y equals B, and z equals C. So 3 coordinates to describe a point in space are 3 dimensions. So that's what we're talking about here, and we want to generalize everything you learned in Calculus 1 about taking derivatives, taking integrals to functions that perhaps graph to be surfaces or curves in 3 dimensions. Okay, so anyway, that's what you're up against. Okay, so rectangular coordinates in space. To construct our 3-dimensional coordinate system, which we call R3, we draw an axis, usually called the z-axis, so that it's perpendicular to the xy plane. And of course, it runs through the origin. In this class, very important that you realize, and that everybody does it the same way, otherwise it's confusing to look at. So the origin would be where, according to Homer, maybe right below his neck. I'll make the point big. So the x-axis would look maybe like that, right? Got a little different orientation than I drew a few minutes ago. Or location, anyway. So there's positive x, positive y, and positive z corresponds with Homer's head, right? Notice that his right arm, so stand like this, notice that his right arm corresponds with the positive x-axis, doesn't it? And his left arm corresponds with the positive y-axis. It's called a right-handed system, okay? And so even though you could easily relabel this guy as y, this axis as y, and this axis as x, we don't do that. You have to keep a right-handed x, a right-hand coordinate system orientation in this class. And it's just a nice way to standardize things to make sure everybody does things the same way. And you might say, well, this looks different than the picture you drew above. But if you think about it, okay, if you drew his arm here, right arm here, and left arm here, his head would be here. It really is still a right-handed orientation, a right-handed positive x-axis, right? A left-handed positive y-axis. So pretty much the rule in this class, I won't say every time, but almost every time, we keep the positive z-axis going up. And then you can rotate the positive x-axis and positive y-axis as needed to draw a good picture. So really what's happened here is if you go from this picture to this picture, all I've done is I've rotated the x-axis over to here. It was kind of over here. I've rotated the x-axis over here. But it's still the same orientation as far as the right-handed orientation goes.